All right, welcome to Vitess V3 session 6. Just to recap what we did last time. Last time itself was a recap of somewhat of a summarization of the previous sessions. We went through an elaborate example that involved subqueries and slowly built upon this story about how various relationships get formed and used. We could summarize those relationships, I guess, here. Um, um, so when we start the parsing process of the original AST, we usually start with is where the green is kind of the starting point of our data structure. So we start with the original AST and then build a primitive, and then push AST elements into the current primitive or whatever is underneath. And all other data structures are found from originate from the primitive to other parts. There are basically three worlds that point to each other in our building of the plan. That's one is the primitive world, which is the starting point. And from the primitive, especially the route that points to the AST world. This AST world is different from, is slightly different from the original AST because this is actually a subset. But actually, we reuse elements of the original AST. We just pointed them. But technically speaking, this is its own AST that will be used for generating the code. And we have the symbol table world, which says that every route or every primitive points to a symbol table, and that symbol table has symbols in it. And those symbols could point back to either the current primitive or other primitives that may or may not be part of the current one. And that information is used to decide later whether we need to substitute the AST nodes with bind variables. The stuff that I did not cover in the data structures are things in the wire up phase, because that's relatively simple. And we can actually cover that while when we drill down in the code, which is going to be what we are going to do today. We did have a small preview last time, but today we can do a more involved deep dive. Any questions so far?
Nope.
Sounds good. Okay, so I now have the builder file open that I showed last time, which is actually under VTGate plan builder, which is the main entry point. These are the files in the plan builder, and let's start with the builder. So in the builder, the main entry point is both build or build from statement, and build calls build from statement. And as you can see, union is unimplemented. So when we start to implement union, we'll break this out and add some functions here. Build select plan is pretty much what I've been covering the entire last week. I did not cover insert, update, or delete. That's because they are relatively simpler. They have their own complexity, but they're not as complex as select, mainly because of subqueries and joins, which these guys don't have to deal with. So if you jump into build select plan, it's a function that actually shows what the high-level process. One is first we process the select, and then after we process the select, we build the new join table, which is the symbol table for joins or the wire up phase. And then we do the wire up. And once we finish the wire up, we extract the actual primitive out of the builder primitive. So there is actually, like I mentioned before, there are actually two parallel worlds / data structures. The reason is because when we build the plan, each of these primitives actually has additional metadata that is needed to figure out, like, for example, pointing back to the symbol table, right? So you need to say, well, what's your symbol table? So those pointers are extra. They are actually not needed in the final plan, but they are needed while we build our plan. So basically, every primitive that we have has actually two versions. One is the runtime version, which is the engine version, which is just what is needed to execute the command. And the other one is the builder version, which is the build time version, which is obviously a superset, which actually contains additional metadata for us to uh, resolve things when we build the plan. So if you look at it here, I have, for example, a route.go here. And if you look inside a parallel tree, which I call the engine, you see a route.go here. So, and you see a join.go here, and there is a join.go here. So that's something that you have to keep in mind. So because of the fact that these are parallel data structures, the names are overloaded. So inside Plan Builder, I call it a route, but it's actually the route, the plan builders, the builder route, or the route builder sometimes is another name that we call it by. And same thing is in the join inside the plan builder is the join builder. What else? I think that should be enough for us to get started. So like I mentioned, the first thing we do is analyze the from clause. After the, you'll see the high level flow here. Okay, so the reason why I wanted to explain that is because when I say builder, that's basically either a join or a route. And when I say dot primitive, this is the function that extracts or builds the actual engine primitive that is returned to the caller. As you can see here, I have engine.primitive, whereas the process select returns a builder. So that's the difference between these two. So otherwise, I don't think the only place I would reference to engine.primitive is when I actually do the final, during the wire-up phase, when I convert ASTs into SQLs. Otherwise, I don't think we will talk about this primitive usually. So, so we look at the first thing like I mentioned, we analyze the from clause first. And after we analyze the from clause is when we set the outer symbol table of the local one. The reason is because MySQL does not allow you to reference symbols outside. If you have a subquery which is inside the from clause, you cannot correlate it. Basically, you cannot correlate it with things that are outside the from clause. And the way I prevent it is pretty simple, which is I set the symbol table's parent to the outer symbol table only after the from clause has been analyzed. And the next one is process the where clause, then process select expressions, process the having clause. We basically go one clause at a time. And as you can see, all we try to do is push, 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 push. And if a push fails, then we fail. The only time when we build actually primitives is in the process table expressions, because once our primitives are built, which has routes and joins, those are all built only during this phase. Once this phase is done, the only other thing we can do is push AST elements down to those primitives. And if any of those fail, then our query is not executable. Obviously, if we start to add more primitives, then some of these will actually not be simple pushes. Some of these will end up in more in the tree being grown, our expression tree being grown to accommodate more opcodes. So far, so good. And as you can see, process table expression returns only a builder. And this basically says that the builder is the starting point. And if I want to access the rest of the data structures are accessed by using the builder as a starting point. Like, for example, the symbol table that I need to reach is by saying, oh, builder, give me your sim tab. Sounds good. Right. Let's actually look at the complex part, which is process table expressions. Process table expressions says, I think this part, Brian made some changes here to accommodate more, to accommodate joins, or he requested a feature, which I seem to have done to change it. So what I do is, the first part of a table expression is comma separated operators. So comma joins, that's what we handle. So I say process the first table in your expression, and that is my left plan. And then process the right side of the table. This is a recursive call. As you can see, this function calls itself. So basically, we are doing process the left and then process the RHS, which is, again, recursively process its left and process its RHS. So it'll recursively actually end up processing all table elements. And then what I do is I join my left plan with the right plan. So let's see what this join does. So the join basically is a virtual call. It calls into the interface, which means that the function that will get called depends on what primitive the original plan returned. So if process table expression returned a route, then the routes join would get called. If it returns a join, then the joins join would get called, since joins allow other joins. We should look at, I'm trying to see, let's set that aside. We'll come back to that function. Let's actually drill down what else happens here. Let's see, we drill down into process table expression. Note that this is without the S. This is a single table expression process, and this has plural. It has an S at the end. So the first L plan call actually goes into this function. And this function has the complexity of either it's a simple table expression or it's a join clause, which is a join on, it could be left join, right join. So it could be any of those things. So far, so good. So this function call tree follows pretty much the same tree, the same dependency that exists in the AST. So basically, once you recursively down, at the end, the leaf node will be a table expression, a simple table expression, which is actually which is what we call as an aliased table expression, because it can have an alias where it can say T1 as T. So that's basically, so this is the leaf node of the recursive call. So those functions basically call some other functions or call themselves back, and eventually they reach this table expression analyzer. And if it's a simple table expression, then I say get table plan. Let's look at what get table plan does. Get table plan asks the V schema. Because it's a table, it's a V schema question. I says, okay, find this table in the V schema and tell me which key space it belongs to. Because that's all we know. So the key space could be either sharded or unsharded. Sharded or unsharded, we don't care, because we can always build a route for a table expression, because just a from T means it is select star from T, which means that it's either scattered. If it's sharded, it's a scattered route. If it is unsharded, it's an unsharded route. So this is basically our first node that we built, R0, as we saw in the diagram.
Would it be possible to add or if this makes any sense, to add into here into this function where we actually build the route object, like a variable that says like, is it sharded or is it unsharded? So that as we're further up the space, we can know more easily whether something is sharded or uncharted. Because I mean, I see opcode obviously is different between the two, but I believe opcode can change based on the various analysis that we do throughout the call stack. Does that make sense?
Yeah, we could look at it. The one issue could be is if you did that, you will need different implementations for routes. So you'll have a route unsharded versus a route sharded.
Okay.
So which means that if you go to route.go, so you may end up duplicating functions here, right? So this route, how many lines is this? This is about 500 lines. So this covers unsharded and sharded routes, right? So if you made a separate type for sharded versus unsharded, you may have to duplicate some of these functions. Like, for example, generate field query, right? It is common for all of them. It doesn't care if it is sharded or unsharded. As a matter of fact, we can check if how often this function checks the opcode. See, for joins, it checks the opcode, right? When you have to do the join. For improving the plan, it checks the opcode. For compute plan, no, that's for compute plan, it does check the opcode. It's possible. I won't be surprised if it simplifies the code. Actually, looking at this thing, because all these functions that I see, they are all for sharded plans.
Yeah.
So it could simplify. So you can try pulling unsharded out into a separate route opcode. And if that simplifies the code, that will be a good thing. So the only thing that you should remember is that the unsharded route and the sharded route both are building a normal engine route. You could actually think about separating the engine route also into sharded versus unsharded. And for that, you'll have to look at the opcodes, the implementation of the opcodes inside the engine's route to see how much commonality exists between those two.
Gotcha. Okay. The reason why I was asking is because in like naively looking at this in the past, I always was trying to find some way throughout the code to figure out, like, am I in a sharded or unsharded? Because as you know, we're always looking to add functionality for the unsharded.
Yeah, yep. Yeah. So the one thing, the other issue you may face that may actually be a little more complicated is, you remember I mentioned that a symbol points to a route?
Yeah.
That rule may start to conflict because then a symbol cannot point to just a route, right? Because now a symbol can point to either a sharded route or an unsharded route.
Yeah, gotcha.
So you may have to abstract it out into a symbol points to a primitive rule, and then resolve wherever it tries to access the route. You may have to special case sharded versus unsharded.
Yeah.
So you can try. If I don't know how many places you would run into, but if it's not too many, it may still be worth it. And actually, it's a good idea to do it because in the long run, it's not. This rule cannot be. This relationship cannot be maintained forever because eventually a symbol can be created by something other than just a route.
Yeah. Okay, thank you.
That's a good question. All right, let's close this again and go back to where we were. So we were in select.go and, oh no, not select.go. We were in get table plan. We are in the from.go. Basically, we are analyzing the from class. So get table plan builds a route always. No, not always. Actually, it does. It always builds a route, which is called from process alias table. So this is the first part. And the second part is if it's a subquery. So basically the leaf node of an alias, which is the alias table, can be either a simple table or it could be a subquery. If it's a subquery, then it must contain an alias because that's actually a syntactic requirement. So if it's a subquery, you'll so all that design that we did, this is where it pays off. Because when we see that it's a subquery, all we do is call process select, which is basically calling back the top level select analysis function that actually goes through the entire process that we are currently going through, but just for the subquery. But in terms of contract, the only thing that the process select owes in terms of its return value is the subplan, is the subqueries plan, nothing else. And if you looked at our graph here, when it did a process select, this entire section is what it built. It basically built this full data structure and just returned it to us. And what we do with it, you can look at it here. The first thing we check is that a simple route? If it is a simple route, so basically at this point we say, well, if your subquery is a join, tough luck, we don't support it. But if it's a simple route, yes, then we can. Then the next thing that we try to do is, let's see what we try to do. The next thing we try to do is there any way for the subquery to inherit the properties of the tables or the tables that it is itself inquiring, right? So for example, if a subquery references a column, a Windex column inside the underlying table, then that property is inherited by the subquery. What that means is that we can treat actually the subquery as if it's a sharded table, like the original sharded table, which means that we can make routing decisions about it, and we can do joint decisions and stuff like that. So it's kind of cool. And I think there's some examples that I have for it. So that's what this code does. It basically says, okay, let's find out all the column indexes. And basically what this code does is it builds a logical table and adds it to the V schema. And that includes Windex and everything else, which means that anybody else that looks at this subquery, for them, this will appear as if it's just a normal table. So any operation that can apply to a normal table will work for this one. And this is the clincher. Look at what I did. I said, finally, the subquery, once it is merged with the outer query, we redirect it to the outer query. So this makes basically the plan that was built by the subquery, that plan becomes defunct because the subquery is merged with the outer query. And like I mentioned, at this point, the only thing that we support is that the subquery merged with the outer query. So it points to the outer query, which is the route builder. Sounds good? All right. So basically, once process table expressions, we haven't done yet. So we have to look at the join. There are two joins that we have to look at. The first join is what happens when this join is implemented by a route versus what happens when a join is implemented by a join. Let's go to route. So here's the join code. Should be fairly straightforward. So it says, okay, I am a route. Let's look at what is on the right-hand side. Is the right-hand side also a route? So if the right-hand side is not a route, then I give up. I give up as in what I'm saying is that I assume that I cannot try to merge them into the same route because the right-hand side is already a join. So what I do is I say build a new join route, a new join node using my current route and the left-hand side and the right-hand side join. So if you have a so the right-hand side is a join tree, the left-hand side is a route node. The outcome is a new join node that includes the left-hand side route and the right-hand side join. So that's what this line of code does. We can actually look at new join. So new join says, first merge the symbol tables. We went through this last week, so this is the code that performs the merge, where everything, all symbols from the right-hand side symbol are added to the left-hand side symbol table. And there is an error check, which means that if there are duplicate symbols, then merge is not allowed. So it basically detects duplicate symbols. And I point the right-hand side route, the right-hand side join. I say now point it to the new symbol table, because it was pointing to the one, to the RHS one. I change the order of all the routes. That's a recursive function. So if it was R0, it becomes R1. And what else do I do? And then I say that I assume that it's a normal join, but then if it is actually a left join, I change it to a left join. And let's see what else I do. Then I build the join node. And where is the right join? I remember handling a right join. There's a place where I handle right join. We'll probably encounter it. So if it's a right join, what I do is actually flip it. Make it make the LHS the RHS and the RHS the LHS, and then it becomes a left join. Basically, I convert right joins to left joins and then join them. Okay, so we do. So if you see here, if it's a left join, I always push the on clause to the right-hand side of the tree. So that's actually how joins work. The difference between a normal join and a left join is that there is no constraint on the left-hand side result, right? The left-hand side result is always returned, whether the right-hand side returns a result or not, which means that the filter, the on clause of a left join is applied only to the right-hand side node. So that's why I push. So if it's a left join, I push the on clause into the RHS, so as you can see here. And not only that, I also say that no new constraints can be pushed into the RHS, because that will corrupt the results. So basically, the way a left join works is that the on clause is applied, is pushed into the RHS, but anything that is in the where clause actually has to be applied after the join is performed. It's almost as if that where clause is like a having clause for the join operation. So to prevent where clauses from being pushed into this right subtree, I mark this right subtree saying that this is an RHS of a left join. Never push anything in here, or be very careful when you do. Not everything is pushable. But if it's a normal join, then the push can go left or right. So I basically apply the RHS rule, the rightmost rule, for pushing this filter. We can look at this again. Actually, should we? We can preview this and then come back to this later. A push filter is basically analyze each expression, postpone subquery processing to the end. We'll come to that later. And it's actually not completely necessary, but that is beneficial. And then for each of these expressions, I find the route and then push it down. That's basically find the route and push that filter into whatever route comes out. And we saw find route last week. It is the universal awesome function that basically accepts any expression and tells you which route it belongs to, using the rightmost rule. Okay. How are you doing on time? 2:30. Good. Still doing well. What else? So we have looked at join that builds this. So this is basically what happens when the left-hand side is a route and the right-hand side is a join. If the left-hand sides, if the left and right key space names don't match, then it's an external join also. So it's the same function that I call. if the left, if the key spaces match, but the opcode is unsharded, then I know that it's actually same shard, right? We don't have to do any more analysis, in which case I call merge function. The merge function actually merges the two routes into one route. So this is the best case scenario, which means that the entire section of the query goes into a single route. What's a join?
So is that to say that anytime so anywhere further after analyzing the table expressions, if we were to see if there's only a single route, that means we're definitely on just a single shard?
Correct. Yes, and you will see me using that rule all over the place.
Okay.
Yeah. So basically, basically, if especially when I'm looking at group by clauses and order by, if I see that it's a single route, then I just send it through.
Gotcha. Cool.
There are exceptions, like for example, group by cannot be pushed to a single route if it's a scatter. So there's always corner cases, no matter how you split it. So if you split it, it may make certain things simpler, but other things may become more complex. I want to see what a join. Oh, a join is I don't know why I call it a join. A join is basically the right hand side of the join. So if both route are sharded routes for comma joins. Oh, comma join is basically a join. I think A stands for no on clause join is probably what it means. So if it's a comma join, then we always build a join because there is no on clause for it. Yeah, I think that's what a join is. I need to find out why I named it a join. I'm sure there is a reason. And then after we do the join, then what we do is we analyze the on clause. The analysis of the on clause is very similar to the analysis of a where clause, which is why you will see that I'm splitting it using as and expressions. And then I check if the left and right route, if any of those constraints identify the left and right route to be the same, then I do a merge. So the two routes merge, irrespective of what else is in the where expression, because you need one constraint is sufficient to say that the two go to the same shard. And if I reach this point, it means that the merge did not. Actually, the merge did not succeed. I was not able to identify that they were the same route. But there is one special case, in which case it is still mergeable, which is the case where both use the same constraint, but differently. So basically, the first constraint checks a.id equal to 5 and b.id equal to a.id constraint. But what if it was a.id equal to 5 on the left-hand side and b.id equal to 5 on the right-hand side, right? So that's a special case, which actually amounts to also a mergeable route, which is actually this special case check. And then finally, if none of that works, then I know that the two routes are not mergeable. Then I build a join node. So this the high-level description of this algorithm is I have the left-hand side, which is a route. If the right-hand side is also a route, see if the where clauses, see if it's unsharded, then they are mergeable. If they are not, if they are sharded, then see if the where clauses are such that they are mergeable. And if they are, make a new route. In all other cases, build a join node on top. Okay. And that's what this join does. We should look at what join does itself, and that be even more brain dead, because once we know that if it's a join, then we cannot actually think about even think about building a route. So this code is very simple. If the left-hand side is a join, I always build a new join node using the right-hand side. So it's super straightforward. Okay. Okay. So this is process table expressions. And once I've finished processing this table expression, let's actually go back to the from class analysis. Oh, we have done the from class analysis, so we should go back to select. Select. Here you go. So once process table expressions is built, we are basically at a phase where, let's see, if I present here, so it basically goes through this part. So this is where we would be, basically. No, not, yeah. So this is the point we reach. Oh, hold on. Sorry. I confused you. There you go. So this is what you have at this point. So you pretty much have the entire tree built. We have the symbol table in place, no call sims. And we, in terms of algorithm, my analysis just exited this part. And we are now going into the where clause. Actually, this would be more like it, yeah, because the on clause has already been pushed down. And as I hinted here, there is not much difference between how an on clause is handled versus how a where clause is handled. There is a lot of commonality between them, and there is a lot of common code between them. So if you look at push filter, it does something very similar to what we do when we analyze on clauses, except that it's always pushed as a where clause. When you push an on clause down into different parts, then it gets pushed as a where clause. The only place where an on clause doesn't get pushed as a where clause is if two routes merge. And so in that case, it also inherits the on clause as part of the subroute. And what else? Actually, this is a good time to go into push filter. Let's go look at find route, which is the most complicated function in, I guess, the most effective function. It's actually not very complicated. It's probably 100 lines. So here what we do is in find route, we call walk. You are familiar with the AST's walk. All it does is walk through every node and call your function back. And here all we do is, if the node is a column identifier, it's a column name, I ask the symbol table, tell me which route this symbol belongs to. And symbol table returns a route name, a particular route. Then what I do is, if the order of the route is greater than the highest route I have seen, I update the highest route to it. So basically, this is how I find the right-handmost route. And that's it. Once this function exits, then I have a final route that I can push this expression to, and I push it. When can this fail? This can fail if we have a subquery that is not mergeable, right? So that's basically this part where if it's a subquery, then what I do is I say, analyze the subquery, which builds the entire subtree, and then returns me a plan. And then what I do is I check if the subplan is a route. If it's not a route, I say, sorry, not supported. But if it is a route, I look at all the external references that this subquery had and find out the route for each of those. And make sure that I compute the highest route only for those that belong to the current symbol table. If a symbol was outside of the current symbol table, namely its parent, then that is not taken into account for mergeability. And at this, I apply the same algorithm, which is find out the highest route that all these external symbols reference. And then what I do is for subqueries, I actually build a list of subqueries, because just getting the highest route is insufficient. What I have to do is also analyze mergeability, right, which I will do later, and which is done here. And the reason why this is done later, I believe, is because we want to make sure that a sub route happens only after, because okay, so basically pushing additional where clause items down into these routes could improve their plan, and therefore we want the subqueries merge analysis to happen after all the where clause elements are pushed except for the subquery ones. So basically that's the reason why. Actually, that's also the reason why when I analyze, I actually push subqueries to the right-hand side. So once this function returns, I ask each subquery, can you merge with the highest route that was found for you, with the highest target route? And if the answer is yes, then we do the merge. If the answer is no, then we just error out. And there should be something here. Oh, the redirect. I was looking for the redirect. And if there is a merge, we redirect the current route to the highest route that we found, which basically says that the current route is now defunct. This subquery now effectively belongs to the route, to the parent route. All right. This is the reorder by subquery. So what I do is if I see a where clause, I actually push anything that has a subquery to the right-hand side so that I analyze them later. If you look at push select expressions, it's actually simple also, unless it has issues with aggregates. If aggregates are not happy, then we give up. If you go to select routes, a non-star expression is something like a.call, and star expression is like star. So if I encounter a star expression, this is actually a special case. I allow star expressions if it's a simple route, because if it's a simple route, then I don't need to deal with the columns and stuff. So I can just push down the star and not worry about what's going on. But if there are column references, then I have to do find route and stuff like that. And for now, next val is not supported, but we can add support for it later for the next val construct. And and of course, as you can see, find route is called here. And what you have to note here is that find route does not really care whether it's a select expression or a where clause. It tells you the correct route no matter what expression it is. And I use this for other constructs also, for having and stuff like that. All right. So we have done push select expressions. The rest, actually, you should be able to, at this point, you should just be able to walk the code and understand what's going on. Check aggregates, actually, for example, see if it has any aggregates. If there are any aggregates, then what it does is that it checks that the bottom is a route. It allows pushing of aggregates only if it's a single route. As you can see, is single, right? So the rest of the functions are more or less easy to understand. So we have exactly 10 minutes left. That's awesome. So let's go back to builder, select actually. And let's look at wire up. So the wire up is also a virtual function. Basically, we ask each node to wire itself up. And obviously, guess what join would do if you ask it to do wire up? It will ask the right-hand side to do the wire up and then left-hand side to do the wire up. I think that would be my guess. Let's see. Yep. Go to the right, perform the wire up. And if that worked, go to the left, perform the wire up. So pretty much all the wire up logic is in the route node. So let's go to route. All right, so we found wire up here. What does wire up do is switch. So the first thing it does is if we actually improved the route, right? If there was a constraint like a.id equal to b.id or b.id is equal to a.id, and a.id is an external reference. So when we built the route, we actually put the a.id column identifier inside the route's column clause. But what we actually need to do is replace it with a bind variable, right? So we have to replace all a.id references with aid bind variable, and that includes the route that we built. And the reason why we didn't build a bind variable, as you know, before, is because we can't build it until the routes are all resolved. So this value basically waits till the end. So if it's a comparison expression, then what I do is I say procure the value from. So what I do is if I encounter a b.id equal to a.id constraint, I put the entire node inside this builder, inside that constraint. And then at the end, what I do is I convert it to a bind variable and just put the bind variable as a constraint here. And that is done by saying that ask the route builder to procure a value. And the procure value actually goes up the tree to a common node that from which the value is coming, and then pulls that value from here. So that's actually how it works. And then what we do is we do have to massage the AST that we have built, because there are things to take care of. The first one that we do is sometimes a push down we may end up with no select expression on one of the routes. It is possible select if you do a join, but there is no column that you select from the right hand side, right? If we find that the select expression is empty, then we add a select one. So that's this one. And if it is a comparison expression, what we do is we flip it. If it was a.id equal to b.id, that won't look good when it's represented. So we flip it to b.id is equal to a.id. So that a.id then it becomes a bind variable. It reads better. And someone said that even MySQL treats it better. So, and then what do we do? Generate the query while simultaneously resolving the values. So I go and replace the nodes with their bind variables, and one node not and I also generate the query. Wow. Okay, that's two things at the same time. So at this point, I'm building the final route, and as you can see, this is the one place where I access the E route, which is the engine's route, and then set it to the query that I generated. I also need a field query. That is because if the left-hand side of a join yielded no results, I still need to fetch the field information from the right-hand side. And that's what this field query is for. And the procure values function is complicated, but it is straightforward. It essentially finds out the source of a value, find out a common node between them, and makes the left-hand side supply that value and the right-hand side procure the value. And that should, and rest of the functions are all support functions. If we went back to the builder, you will now see why we have all these things. As a recap, the symbol table is the symbol table that this primitive points to. You can change it because when routes, when routes merge or come back into a join, then you need to merge the symbol tables. Order tells you what the order of the current node is. Set order changes it. Primitive actually gives you finally the underlying primitive that was built for the engine to execute. The leftmost returns the leftmost route of the current node. This is for joins mostly. If you call it for a route, it returns itself. I think this is used for something. We can see where it's used. I don't remember anymore, but it's needed somewhere. The join builds a join node using not builds a join node, joins the right-hand side with itself. It could result in a new joined route, or it could be a new join node. Set RHS, we talked about this. This is for left joins. Push select is for pushing select clauses down. Push order by null. I think I did this for Amit because I think this is allowed only in the case of uncharted routes. And various push functions, push select, push miss, and then there's the wire up, which we looked at. Supply is for the left-hand side, and there should be a procure for the right-hand side. Or maybe the procure is only for the route. Yeah, I think procure is only for the route because you don't have to procure. Supply is sufficient otherwise. So this is basically, I kind of rushed through it a little bit, but I think I've given you enough to kind of navigate this yourself. What we can do next time is, which should hopefully be our last session. I may or may not have time to rehearse. If I do, I will rehearse. But what we'll do is we'll go through a mock implementation of a union. So I'll basically type code in there saying that I'm changing here to do this, that to do that, and etc., etc. It's probably not compilable, but you can use that as reference then to do your implementation. Sounds good?
Yep, that sounds good.
Wow, I just noticed that this was a complete monologue. But, I wouldn't have known if you had fallen asleep. Yeah, I have a feeling tomorrow will also be like that, but it's the nature of code reviews. And make sure, and you can actually try to browse through it. And if you have any questions, you can ask them during next session.
All right, sounds good. Thanks a lot.
All right, I'll see you all tomorrow, same time.